finite automata for regular languages, and for context-free language it is non-deterministic push-down automata, right? And you can create a subclass as unambiguous languages. Right, and you have specifically two types of them as practical examples. That's why I took that example. One is LLK and one is LRK. And obviously the unambiguous part, this part, um, this portion deals with a machine that's called the deterministic counterpart of the non-deterministic push-down automata that I am talking about. So I will talk about this later. And essentially, I'm talking about this class, this whole class, non-deterministic push-down operator, right? And I hope from the last classes you have understood the basic structure, the formal notations, and everything, right? Is it? So today I'm going to actually come back to this language onion and show you and give you some very important, very important. I'll talk about some very important proof, and that proof is obviously based on construction. By now, you have understood how to build proofs on construction. So, what is that we are going to prove? We are going to prove that a language is context free. A language is context free if and only if there is some push down automation that recognizes it. Right. So we are going to prove this whole thing, that a language is context free if and only if there is a push down automata that recognizes it, or you can say that parses all the strings of the language. Right? So since it's a if and only if proof, it has obviously two parts. One is you are given a context-free grammar whose language is a context-free language. So I write L bracket CFG. So you are given a context-free grammar whose language is indicated by LCFG brackets. That means a context-free language. So this whole thing is a context-free language. So if you are given a context-free grammar, then we need to show that it has a push-down automation that recognizes it. So we should be able to build a PDA that successfully parses all the strings of this language. So this language has many strings. So we are going to build a PDA that would accept, or that would recognize, or that would parse all such strings. Right? This is one part of the proof, the if part of the proof. And the only if part of the proof is just the opposite, that you will be given a PDA and there is a language of the PDA. So given a push down automation, we should be able to construct a context-free grammar that recognizes the same language. So given a PDA, we should be able to generate the same language with the equivalent context-free grammar. This is the second part. Now this second part is bit counterintuitive. And I would say more complex. So today we are going to deal with the simpler part, and this part is that you are given a CFG, and so that context-free grammar has a language denoted by LCFG. That's a context-free language. So is it possible to have a push-down automata? The answer is yes. The answer is yes, and since the answer is yes, we denote that, okay, for CFL we have the machine equivalent as a non-deterministic push-down automata. Now remember, whenever I say push-down automata, by default I mean the non-deterministic one. I said in said in the last 3 classes, right? So the approach I would take is take a grammar, the most practical way, and the approach is that I would take a grammar, and I would show you what exactly is meant by building a PDA for a context-free language. That is the language of a context-free grammar, right? So that is what I will do. So let us take an example grammar G. Let us take a grammar G, and let us have productions like this: S goes to BS, or S goes to A goes to 0A, epsilon, B goes to B1, 2. So obviously the as it is seen from this grammar, this is just an example grammar. So what we are not going to do is not going to indulge in the structure of the grammar. We have kept beta to be free. Remember, we have kept beta to be free. Here beta is a single non-terminal. Here beta is two non-terminals. Somewhat what Chomsky normal form was talking about. Here beta is a terminal followed by a non-terminal. Here beta is two terminals, two non-terminals followed by a terminal. And here it is a single terminal, right? So we are not concerned about the structure of this grammar as a whole. We are just going to take an example of this grammar, right? Is my board visible?
Yes, sir, it is visible.
Yes, sir.
Yes. 1 minute. My pencil stopped working. I don't know why. Just give me a minute. Just give me a minute. I think I need to restart my iPad. I'm coming back in 2 minutes. Okay. Yeah, it hanged. Right? Yes. Am I audible?
Yes, sir.
Hello? Yeah.
Yes, sir.
Thank you for bearing with me. Let's check whether the board is lost or not. By the way, I am sending you the SVG copy of the board. Do you know what is SVG? It stands for Scalable Vector Graphics, and it means that you need a platform to run that uh, SVG code, and your browser is that one, right? So you need to download that transcript and open in your browser from your computer, right? It may not work with phones. Okay, so let us come back. So this is an example grammar that that I have taken, and we are not going to indulge into the structure of the grammar. We are not talking about the structure of the grammar, right? We are not interested in the structure of the grammar. This is a context-free grammar. Done. Now, what exactly is meant by this proof? This part one of the proof, that given a context-free grammar, the language that it generates, that is LCFG, for that language, it is possible to build a PDA to accept that language, right? To recognize that language, or to parse all the strings of that language. So if you have strings S1, S2 of this language, this PDA would be able to parse all the strings of this language. This is what we are going to do by construction, right? So this is what is given. This grammar is given, and we have to build a PDA. So since I'm talking about building a PDA, obviously this proof is a proof based on construction. So what is that we are going to do? We are going to check whether how to build a PDA that would recognize all strings of the language generated by this grammar. So this is a CFG. So it has a language, right? And that language consists of all possible strings generated by this grammar by using the productions. These are the productions. You use the productions and generate all strings. For example, there is a string 221 that is generated. Got my point? Now we'll take such a string and check whether the PDA that we have built is able to recognize this string, and whether it is able in general to recognize all the strings of this language. So the proof based on construction must be of its most general form. Now let us check, what does a string 221 mean actually? What does a string 221 being generated by this grammar mean? It means that you take a derivation, you start at S, right? You take a derivation, and you go on deriving by applying the productions. And the most general way is you should be taking either a leftmost derivation or a rightmost derivation, right? So I would take a leftmost derivation, and I will show you how to generate 221, right? So I apply S goes to BS, I apply this production, and I apply S goes to BS, and then I apply leftmost derivation. Means every time I'm going to derive the leftmost non-terminal, I am going to exhaust the leftmost non-terminal to give birth to a terminal, and then only I will look to uh, the non-terminal that is towards the right of the leftmost non-terminal, right? So that is what is meant by a leftmost derivation. So by from B you can apply BB1, right? So I would apply BB1. So this is how I reduce. I apply B goes to BB1 followed by S, right? And then I again take the leftmost non-terminal B in this case, and I apply B goes to 2, right? So I apply B goes to 2. So now I have 2B1S. So in this sentential form, B is the leftmost, right? So what I will do is I will write 2, and then I will again reduce B, this B to 2. I apply B goes to 2, right? And then I apply 1 as it is, and then S. Now in this sentential form, you have 3 terminals followed by a single non-terminal, and so it is the leftmost non-terminal. So I apply S goes to, say, S goes to A, right? So I apply S goes to A. So you have 2, 2, 1, and S now goes to A. In this sentential form, you have A as the leftmost non-terminal, and you apply A goes to epsilon, right? A goes to epsilon. So you have 2, 2, 1 epsilon, and that is nothing but 2, 2, 1. Now this is the I have written like this, but always you can draw a parse tree, right? There is a parse tree representation. Actually, this is a parse tree representation. I have drawn like this. If I would have drawn something like this, S goes to B and then S, you will always see that the leftmost is B, B, 1, and S remains. So it becomes 2, B1S, right? And then this, and then uh, and then after this, so this is one sentential form. This is what I'm saying. This is one sentential form. And in this sentential form, this becomes the leftmost, right? So here it becomes leftmost. Okay. So now our duty is to have a push down automation that would recognize this. Now, how it would recognize? If you remember the push down automation um, machine diagram, so you have an input tape closed on the left. You have a finite control. That means you have a del, right? And you have a stack. That is what you have in a PDA. What are the operations on the stack? Read and pop and uh, push, right? And we allowed epsilon to be everywhere. In case of the input, we allowed epsilon. In case of stack, we allowed epsilon. So this is essentially your PDA. So if I want to check how to build a PDA, what you are given this string, right? So this is what you are given. That is, you are given a string, and you have to check that okay, this string is being accepted by a PDA. So that means, in other words, that we are able to design. Again, my board is hanging. I don't know. Just give me a minute. I don't know what is happening. Please bear with me. Such things are not in my hands. So if that is the case, that means you have been given this string 221, right? And you are required to check whether this string can be accepted by a PDA. So this string is the input string that you have been given, and you have to check whether you can use this input string, this input tape, and a stack, and design a del so that this gets accepted. Got my point? So that is what you have to do. So you have been given 221 in your input tape, and you have been given an empty stack. So you have to design a del such that it accepts this string. That is what your objective is, right? So what I mean is, now look to this sentential form. So let us concentrate on this sentential form. Let us look to this sentential form 2B1S. So this is why I call it a sentential form, because this is at some middle point of your total derivation, somewhere in between your total derivation. So if I look to this sentential form, what it means is your your configuration of the machine should look something like this. It should be having a 2, and your stack should be having B1S, right? B1S. Such that taken these two together, This is the finite control. Taken these two together, you are in a scope to expand this B further, right? So what is the input? What is the input that you started with? The input is 2 to 1. The input was 2 to 1. For example, you are resting on this 2 in some middle point of your um, uh, computation. You have consumed this 2. That's why I have written in red, and this is a stack. So that the input that has been consumed and the stack together is your sentential form, right? So that the input that you have already consumed followed by the stack gives you the sentential form. So if I represent this picture in somewhat like this, so let this was the input that you started with. Let this was the input that you started with, and this was a stack that was empty. And in some middle point of your computation, you have consumed this. So your head is now resting here. This is the finite control, and the stack has B1S like this. So the idea is that this 2 along with this B1S, if I draw the stack, if I invert the stack, something like this, let me draw the finite control at the top, and I represent the input something like this. 2, 2, 1, and what I do is I rotate the stack. I rotate the stack something like this, and I represent the stack something like this. So you have B on the top of the stack, you have 1, and you have S, and you may have optionally a dollar. So what I mean is the 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 symbol that has been consumed followed by whatever is left on the stack yet to be resolved together should conceptually give you your sentential form. So this is 2 followed by B1S. And this is exactly the sentential form that 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 I took as an example. So we are deriving 2 to 1 starting from S, and somewhere in the middle we have 2B1S. Now, that middle portion, that intermediate portion, I am representing how your PDA looks like. So to generalize this, I can say you have A, B, C, D called terminals followed by some string gamma, right? Why gamma? Because that string may be both terminals and non-terminals. So I can write something like, to generalize this, A, B, C, D, E, these are terminals, and for example say B, B, A, B, C, C, A is the stack contents. Okay, got my point? So this is the most general form of representing what is there in your input, what is already being consumed, and what is what stack is still left. Now from here, it's again hanging. Please give me a minute. So what is the most basic part of the algorithm when you design a PDA? So since you have pops and pushes, the most basic thing that you intend to do is a match, right? Whether it matches your top of the stack. For example, in the last classes, I've shown you the popular example of 0 and 1 and we talked about matching. For example, we matched something in this state Q2, right? Yeah, I hope you remember. So keeping that in mind, what we can say is that if this is the interim situation of your PDA that we are going to design and generalize in the most general case. So what we would be doing is This is how where our head rests. This has been consumed. The next input symbol is 2 and the top of stack is B. Now we would try to find out where B goes to, right? Beta 1, beta 2, B may be going to many betas, beta 3, for example, in your grammar. We'll try to find out where B goes to and then expand B to the right hand sides, pop B and replace with the right hand sides. Continue doing that in the leftmost derivation case as I have shown you. Continue doing that, right? And then hope that you have arrived at your stack containing this particular symbol on the top of the stack after many steps. So you can say that after many steps I actually have this B has been reduced to 2 uh, 2 1, for example, something 2 1 capital C, and then you have 1 and S as you have 1 and S. Now once you have a 2, these 2 and these 2 matches, so you apply the matching algorithm and you say that okay, this 2 has been recognized to be a valid symbol. So you are recognizing one symbol at a time to recognize the whole string afterwards. So then you pop, right? Then you have a 1, for example, it matches, it matches. Then you have a C. Okay, you need to find out whether C goes to epsilon, and if at some point of time these tags become empty and your input is scanned, it means that your design of PDA is successful, and it needs to be successful for all such strings. If you need to generalize the case that uh, uh, the languages of CFGs always has a push down automation, right? So what I mean is, for example, let me say it again. So you have uh, push down automata finite control. That means you have a del, and that del is looking to input. That input may be A B C D, for example, A B C D E F terminals, because the input is always a string. A string means only terminals, right? And for example, your head is resting on this C right now. Your head is resting on this C. So you need to, and this portion is checked that okay, for this portion we can accept a we can accept a B after an A, and with the stack. And currently the input is resting on the C, and the stack contents, if I invert the stack for your understanding, I have let me write the stack like this. So this is the top of the stack, and the stack, this is the bottom of the stack, for example. And you have something like a B C on the stack as leftover, yet to be yet to be yet to be operated on. Then you hope that actually when you replace A with some right hand side and continue replacing that A with the right hand side in a leftmost derivation way, the top of the stack would at some point of time reveal a C, and then that C and the top of the stack should be matching. And um, then you say that okay, if it matches, I can proceed and say that okay, I have consumed C, and now let us look to D. So what the idea is that you have to apply some right hand side and replace A. For example, if A goes to B A C, then you have to do some operations so that the stack looks something like this. So stack should be looking BAC, because I have replaced this A with this BAC, right? And then the leftover is same as ABC dollar, right? And then again check what are the right hand sides of B. For example, B has a right hand side C. Now your stack could be looking something like this: small c, small a, small c, A, B, C, dollar. And now you again check, your checking algorithm continuously runs, and you again check that, okay, I had a C in the input for which I was exploding the stack by applying productions, right? And now I have a C on the top of the stack. So the matching part matches. And once it matches, you advance your tape head to D and say that the prefix of this string A, B, C, D, E, F, the prefix of this string in terms of the substring ABC has already been recognized by the PDA. Okay? So what do you have to do? You have to match the top of stack to a rule, P rule, production rule of your grammar, right? Pop if terminals match. Why terminals match? Because your input is a string and it's a string of terminals only. So your input tape has only terminals. So pop if the terminals match. That means the terminal input, the terminal that you are scanning in your input head should be matching the terminal that is now generated by applying multiple reductions on your stack. Right? Pop and then push the right hand side of the rule on the stack. Right? Yes? Got my point? Okay, so rather I have written something jumping step. I should not be writing this one. Rather, I would say that I am writing this operation, the stack operation. So what you are doing, you are finding a left hand side, for example A, you are finding a right hand side. So before doing that, you pop the top of the stack, the left hand side. It's a context free grammar, so the left hand side is always 1. Pop A. So what I mean is pop A and push BAC, right? Push BAC. Push the right hand side of the rule onto the stack. Make sure that you insert backwards. For example, what I mean is if A was going to be a C, when you replace A on the top of the stack, so this is the remaining stack, I am not interested now. If I want to pop this out and replace this A with a BAC, I should make sure that B remains on the top of the stack. So I should be popping A and then I should be inserting a C, right, backwards. Then I should be inserting a and then I should be inserting a B, so that my top of the stack is B now, because I am going for a leftmost derivation, right? Does it make sense? Backwards. Now, once this is done, you repeat. Let me number these steps. 1, 2, 3. So repeat 1, 2, 3. Now remember, non-deterministically until the top of the stack, the step that I had already written here. I wrote something that I'm writing here because I was jumping steps, may be difficult for you. So repeat 1, 2, 3 non-deterministically until the top of the stack has a terminal that matches the input symbol being scanned. Right? So we'll go on. We'll go on similarly as we reduced A to BAC. We'll check for the production right hand sides of B and reduce B to something else, some more string, and we'll go on doing this operation until and unless we have we have for example C, the symbol that is being scanned, that was being scanned on the top of the stack. So ultimately, if you have a symbol C on the top of stack after a finite number of steps, then only your matching algorithm. So after a finite number of steps, you have the small C on the top of the stack, right? and then this C matches the input, and you say that okay, this matches, so I can say that okay, we have consumed up to C. Does it make sense? Do we understand? Yes or no? Yes or no? Yes or no? Now, what is that we are going to do? We have been given such a CFG. We are considering the language generated by that CFG, and we are going to build a PDA. Now remember, this PDA always means a non-deterministic PDA unless and otherwise I state it to be deterministic forcefully, right? So what to do? So we need to generalize, right? So we need to generalize all the things that I exemplified right now. So LCFG for the language of a CFG, if you need to prove that the language of a CFG is exactly the language of some PDA, we need to generalize our example. How to generalize? And then we generalize in terms of rules because it's a CFG. So a CFG should always be having a rule of something like this. A goes to B, A, C, for example. Right? This is a context-free grammar. So the left-hand side is 1 and right-hand side can be anything. So in order to generalize the example that it should be for all grammars, we generalize like this. The most acceptable way out is to think about a general production, right? So this is the most general production. Some A goes to some capital B, small a, capital C. We want to add this rule to build our PDA incrementally. How to do? Very simple. We are in some state Q. I change the state to P. I ignore what I see on the input. Remember, I ignore what I see on the input because why? Because I see a non-terminal on the top of the stack. I see A on the top of the stack. So I should be ignoring what I see in the input. I should only consider what I see in the input if the top of the stack is also a terminal. So for now, I ignore that. See how I generalize. I ignore what I see on the top of the stack, and I ignore what I see in the input because I see a non-terminal on the top of the stack, and then I would apply the right hand side. Now, what is this? Just remember the last class. What is this? This was encoded something like this. That this is the input symbol scanning mechanism. This was the top of the stack, which will be popped off the stack, and this is what should be pushed in the stack. I hope you remember. So we generalize the example in this way, in the most acceptable way. We take a most general form of production and we say that if the top of the stack has a non-terminal, then don't look to the input what you are scanning. It doesn't matter. Keep your head there stationary. For example, in the example, what did we see? We see that it was A, B, C. For example, we were stationary on some symbol C, and on the top of the stack we have A. Now, if we have a non-terminal on the top of the stack, you ignore what you see in the input because you cannot match a terminal with a non-terminal. You have to wait such that this non-terminal actually yields a terminal in some future steps. So by epsilon, I mean ignore what you see. You don't change your head position because whenever it will be required, I will be scanning what I see. But now ignore because there is a non-terminal A. Pop that non-terminal and push the right hand side of the rule. This is a rule. And if this rule is the rule in its most general form of a CFG, then we can see that this design of PDA is also most general. Do you agree? Yes. Now here is a problem. The problem is we have to push BAC in the reverse order. Right? So if I take if I magnify this, this is actually some q from some q1 you are going to some Q2, and from some Q2 you are going to some Q3, and some from Q3 you are going to some P. Right? Now let me explain what I mean. So let me zoom out a bit. So you have to push BAC but in the reverse order. But in the definition, formal definition of PDA, the del was defined as Q cross sigma epsilon cross tau epsilon taking you to 2 to the power Q cross tau epsilon, right? So you were allowed in your PDA. That's why, remember, that's why I told that this formal definition of this PDA is the most primitive one, right? Because you are allowing to check a single top of the stack, and also you are allowing to push a single symbol. So either you have to change this to Q cross sigma epsilon cross tau epsilon, because here I am checking the top of the stack, it's a single symbol. But now it should be going to Q cross tau star. If I say that, okay, I change my primitive definition to a more general definition with tau star, then only you can say that, okay, I can allow a push of 3 symbols, because 3 symbols make a string. So you have to allow pushing a string. So I've changed tau epsilon to tau star, right? Now, what actually this means? This was the formal part. Leave it. What actually it means? It means that, see, we are ignoring what I am seeing in the input. Why I'm ignoring? Because the top of the stack is a non-terminal and my job is not over yet. I need to apply many times the right hand sides of each leftmost symbol of the sentential forms, and then actually I hope that a C is revealed on the top of the stack, and then I will read C and match, right, and then pop. So I have to push this, I have to pop A, and I have to push BAC in the reverse order. Now, in spite of the fact that you may represent this with a tau star, this is what actually happens. So I magnify this with a magnifying glass. I magnify this cursor. What happens? So you are in Q. What you are doing is you are ignoring the input. You are seeing a and you are popping, and you should be pushing this C, right? You are pushing this C. Got my point? Now you are ignoring what you see, right? You are ignoring what is on the stack, and you are pushing this A. Then you are ignoring what you are seeing in the input as usual. You are ignoring what is there on the stack, and you are pushing a B. So these 3 steps is happening when you actually say that I replace the top of the stack symbol with a string. This is what actually happens. This is what should actually happen in your design. And this only ensures that in your stack you push a C, then you push a and then you push a B. So if your A was BAC, you push in the reverse order, so that to facilitate a leftmost derivation, your B is on the top of the stack. Got my point? And you hope that at some later point of time, you have a production that gives B goes to small c, so that you can pop this B and replace it with a small c. And now you can match with your matching algorithm that if the input matches, so for example, you are in some state, say K, so your input is C, your top of the stack is also C, small c symbols, then what you do is you pop, you don't push anything, and change state to L. And since you change state to L, you also advance the input one symbol to the right and say that, okay, I have consumed the C, because that C actually occurred on the top of the stack. Yes or no? So this matching algorithm, so let me denote this matching algorithm as a mega state that matches. So it should be looking something like this. It should be looking something like this. For any arbitrary symbol A, should be A followed by A going to epsilon for all A element of sigma. This is a mega matching state. So once you have the mega matching state, you can say that, okay, my final machine conceptually is generalized something like this. As usual, I would start at Q0. And what I would do, remember that I have been given an input string and I have been given an empty stack. So I just ignore seeing the input string. My first step is ignore seeing the input string. And if the stack is really empty, I would put a dollar there. So that's the end of stack marker, right? And then I change state to Q1. In Q1, what I would do is I would ignore the input, I would ignore the stack, and I would push the start symbol. Remember, your grammar has a start symbol, right? I would push the start symbol. In Q2, what I would do is I would take this matching step, right? But before this matching step, okay, let me write another step. In Q2, what I would do is I would ignore seeing the input. I would ignore seeing the input. And for all non-terminals, I start at A, S. For example, S goes to A, B, C. So eventually I would get a on the top of the stack, right? The mechanism that I had showed you. For all epsilon, I would ignore seeing the input, because the input is a symbol, is a terminal, and I have a non-terminal here. And I would reduce all non-terminals by something like with right hand sides in an inverted way that I had shown you. And then either I can stay there and do the operation, or I will change state to Q2 for a matching state. So Q2 is my mega matching state, and that matching state is nothing but the input symbol A followed by the top of stack is A. If they are same, then I pop, right? And for all such rules in your grammar, this is the most general form of all such rules, right? Most general form. Clear? So you match, and once you match, you expect that your stack should be empty after you exhaust the input string. You have to ensure that your stack should be empty after you exhaust the input string. So either you go and accept via a final state, or ensure that, okay, I go to a final state and accept, but I ensure that my input is exhausted. Now this epsilon is interpreted as, you can interpret as either you ignore what is there on the input because there is nothing on the input is exhausted, and the dollar is revealed, and what you do is you just pop the dollar. So you started here with an empty stack and the input string, for example A, B, C, and here you end in some final state. Here you end with the input, the whole input A, B, C being parsed. This whole input is being parsed, and there is epsilon at the end. This may be one such interpretation, or you can interpret that, okay, I'm resting on C and there is no more right, there is no more symbol on the right, and I ignore epsilon. That's your interpretation. And your stack is empty, it has only a dollar. So epsilon dollar, I pop this stack such that I give the system the empty stack that the system gave me for my computation. Got my point? So you started with this input string ABC. Pardon me, my board again hand. Okay, so it doesn't matter. I've completed the portion that I wanted to talk. So you started with an input string ABC and an empty stack in Q0, and in QF, after doing all these, after realizing all these derivations, after realizing all these productions, in the most general form of the grammar, you generalize the moves of the PDA also in its most general form. And since by keeping the sanctity of the general form, you are able to picturize the PDA flow, you say that, okay, for all CFGs, it's possible for if if you are given a CFG, it is always possible for you to design a PDA. Now, are things clear? Yes or no? I tried my best to make things clear. Are things clear?
Yes, sir.
Clear?
Yes, sir.
Nobody is talking. I want to listen from other people also.
Sir, my voice is not audible.
Yeah, your voice is audible, but I want to listen from other people also.
Oh, okay, sir.
Nobody is talking to me. Yes. I want to ask you, did you understand what I meant to say? Yes or no?
Yes, sir.
Yes. Thank you. So give me a class on Monday. I have still some portion left before I hand over to Professor Roy. Should be taking from Tuesday. So give me a class time on Monday, 1 hour class time. I want to wrap up something. Vasu,
Yes, sir. Then from 5:30, sir.
from 5:30, will it be possible if you give me? Okay, from 5:30 it's fine. So please give me 1 hour time from 5:30, and from Tuesday, Madam is going to take classes, right? Okay, bye.
Okay, sir. Thank you, sir.
Okay, sir. Thank you, sir.